Okay, so I guess I got to start by explaining. I didn't want to get a lot into the manufacturing techniques and all the specifics of it, but I'm going to give kind of an overview of what I was working in the summer and everything, and if anybody's got any questions, you can interrupt me or stuff like that. But I guess my agenda is to introduce a little bit of my work at Marshall Space Flight Center and dealing in robotics. And a lot of the stuff that I worked with was with old techniques of manufacturing and also some new techniques of manufacturing like 3D printing and stuff like that. First off, I'm just going to start by NASA's still in business. Just because the space shuttle shut down, they're still building rockets. This right here is the SLS rocket that's being developed by Marshall Space Flight Center. They are planning to go back to the moon on that rocket and also go to Mars eventually. It will be slightly bigger than the Saturn V that was built by Werner von Braun, and but also Marshall Space Flight Center doesn't also just build rockets. They get into a lot of different stuff with science and a lot of stuff within coordinating stuff for the International Space Station, which they're actually a backup center for mission control. If something were to go wrong at Houston, they can shut everything down and run it from Marshall Space Flight Center. And then you can see they also built like the moon buggies and stuff like that in the past. Deep Space Habitat was a concept mission proposed officially in 2012, and it seeks to create a space station, space colony, either at a Lagrange point out in the middle of space or somewhere around the moon orbit to kind of expand long duration missions to so what they want to do is start out with a 60-day mission around the moon and then expand it to a 500-day mission around the moon. But to do that, they need a lot of equipment and they need to develop a lot of new technologies. And so one of the things that they're working on at the Space Center is the development of the flex craft, which is really, in today's day, you see an astronaut in the space station, they'll go out for a spacewalk, but it takes 8 hours approximately for them to get ready, get on in the suit, prepare everything, and actually walk out the dock station and get out there and do their things. So to avoid all that, basically your time in space is valuable and you don't want your astronauts doing tasks that they don't have to. So to avoid that, they come up with the concept of a flex craft, which is a little pod where the astronauts just climb in, shut the hatch, and then they go do some kind of robotic repairs and stuff like that. One thing that we were working with was there are several Flexcraft prototypes that are being built, and we were looking to expand on different ways that a pilot astronaut could control the spacecraft. And what we were working on specifically was to use the Leap Motion device, which is a small device you can buy. It's probably about $80, and you can use it to control your icons on your desktop. But we kind of hacked into their like motion tracking, and we're able to take that data of motion tracking and take it to our robotic arm. And so basically, when you open your hand, your robotic arm's hand expands, and when you close your hand, your gripper grabs your object, and it tracks your movements back and forth. We used a lot of different things that we tested out. One of the big things that kind of held us back was procurement. It took us about a month to get 6 of those servo motors right here. They had to come straight from Japan because it was already a provider for the U.S. government, and the Air Force used those motors for drones and stuff like that. So, and they're the most heavy-duty servos that we could get, and we were trying to even though we're trying to cut weight, we wanted the best things we could get so we could move where we wanted to move. Our system basically had a computer brain that controlled the leap motion device, and that kind of translated all the data of your motions to an Arduino microcontroller, which was the one that actually controlled all the servos for a 4° of freedom arm, which also another thing that we kind of developed was a small sensor that we put at the end of the robot, and it basically every time you came close to an object, it would let you know where you were, and it would slow down the arm so you would not hit anything. I've got a small video right here, and this is not the it's not the final arm that we worked on, but it's our prototype that we tested everything in. And as you can see, he's moving his arm back and forth. That was my partner that I was working with. And whenever he opens and closes, that gripper opens and closes. And right here you can see all the leap motion device data being translated by the computer. And we used Python to basically read the leap motion device and then communicate with the Arduino. So when it comes to the manufacturing of all, we started by going through a whole process from concept design, coming up with different ideas of what we wanted to do, because we were limited to a 2.5-month period. And then we kind of narrowed that down to what would be more relevant to our boss at NASA that was sponsoring us, and what would help them out the most. So we kind of settled on expanding on the actual FlexCraft that he had on site. And so what we built was basically 2 of these robot arms right here. And one of the things about the Flight Robotics Lab is that it's the flattest floor in the world. And it's been there for probably about 20 years, and they don't like nothing touching that floor because it would cost probably about $15 million to replace that floor. And so we were limited to just a 2D motion, which was good because we were trying to imitate space. And in that plane, the docking maneuvers that we were practicing pretty much correlates to docking to the International Space Station and stuff like that. So, but what we did to enhance our motion was we made our arms be able to kind of lift up and down, which would still restrict our motion of our arm, but it would move up and increase your range of what it could reach. And then we basically, they did not have a model of the stuff they had, so we had to draw up all this in either Pro-E or SolidWorks, which are 3D model software packages. And then we had to figure out whether anything was going to crash into each other and the range of motion of the arm. One of the things that we had to consider is, well, we have an arm that rotates. Is it going to rotate and hit the pilot inside the craft and stuff like that? We did a lot of testing with different materials. Initially, we wanted to go low weight, so we practiced with a lot of plastics and stuff like that. But eventually, with the kind of stuff we wanted to grab, it kind of ended up warping and stuff like that. So we ended up going with aluminum. Oh, and another thing that we weren't forced to, but all the actual metal that went into the project was scavenged off of their scrap piles and stuff like that. Here you can see kind of one of the arms pieced slightly together. Here you can see the servos. This was actual pipe that was thrown out of one of their shops, and we kind of welded it together and did what we had to do. First, we started with the 3D models, and then for actual manufacturing, a lot of the parts had to be in the 2D model kind of sheet so the machine could actually cut it. We used a lot of drill presses and saws and welders, But also with the more advanced stuff, we used a laser cutter, a water jet, and CNC milling to produce more precise parts where you wanted your turning to be more exact. And then the newest type of technology that we worked on was 3D printing, which a lot of the parts, like this gripper right here, and then the actual sensor box that I talked about earlier, all the casings for that were 3D printed. And they had some metal 3D printing, but we weren't allowed to play with it. And I guess some of the lessons learned from this whole manufacturing thing was procurement is can hold you back a little bit. You can't always get what you want. And also, we had a whole plan set up of Gantt charts and scheduled tasks per the 2-month period, and a lot of that had to change because not everything was at our disposal, so we had to kind of put in our tasks in between fabricating a fixture for this rocket or stuff like that. So they were kind of doing us little favors here and there, putting our stuff in there. Here you can see, this is the actual Pro E model that we drew, and this is the actual structure put together. The only major difference from that is these air bearings. We had to go with some bigger air bearings, and the way it works, it works like an upside down, like a hockey table, and the air bearings push upwards, and that pretty much cancels all friction. And so in that 2D environment, you can simulate moving in space. And so here you can see the servos that are mounted, and there was a lot of wiring that we had to take care of in the end. Because our boss, I don't think he believed we could get a lot of it done. He just kind of was like, okay, I have confidence in you, you can do it. But then when he actually saw we were getting stuff done, he kind of pushed us to make everything pretty so he could show it to people. Some other work that we worked on, since we were able to build the arm and have it working, one of our, mentors that we were working in with, at NASA they're always at meetings. So they're talking to each other, and I guess he mentioned what we were doing to somebody. And he had a couple of people that were working on a CubeSat, which is a small satellite, kind of like this one. And what they wanted to do is put a robotic arm inside the CubeSat so they could pick up stuff when they were in space. Because one of the things that they're working on is basically have swarms of CubeSats. Instead of building one expensive satellite, you can build a lot of small cheap ones and have like a master brain satellite controlling all the others. We also kind of participated in some spatial studies where they have some mock-up spacecrafts, and they wanted to make sure that it was comfortable for an astronaut to be able to walk in. Then we partaked in some human studies where we were kind of like the guinea pigs, where they had a lot of different lightings and stuff, and it was basically testing our circadian rhythm and figuring out which was the best lighting for. If you're going to have a long duration mission, you're going to have to be able to control your sleep cycles and all of that to be more efficient in space. And then another thing that we were pushing for is to get a microgravity project where we could test our robotic arm in a zero-G environment with their zero-G plane. But I'm not going to say all, but all accessible student project avenues have been shut down because of funding right now. And here's a little bit of the flat floor facility. This is actually the original flat floor facility that was built for Apollo. And this is the new flat floor facility that's in place right now. And I'm not sure if this video is going to play. It kind of shows how the spacecraft moves in the floor. This is basically a docking maneuver, and so it's got a similar base as the craft we were working on. It's a triangular base that's pushing upwards, and then they have air tanks that are thrusting to the sides, and that basically is going to dock with this structure right here, which is basically simulating autonomous docking that you can't always have your pilot docking your spacecraft, so you want to be able to just hit a button and let it do it for yourself. And so if you want to work in that facility, you're not allowed to wear shoes. You can only wear socks or special booties. We had one guy who actually had his wife make him a special kind of flip-flop, slipper thing out of towels and stuff. And because they've got some scratches on the floor because it's been there for a while, but the way the shop manager put it is there's going to be blood spilled if we scratch the floor. Right now, we've been talking with my boss and a couple of the engineers at Marshall, and we're actually looking at maybe having some of our students work in some projects with them to help them develop stuff. It won't be as highly technical as putting the rocket taking the rocket to Mars, but it'll be stuff that's more simple that they can have students build, and then basically we get the experience and the learn how to do new things with NASA, and they kind of get a cheaper labor force to help them out a little bit. But also, I guess, kind of in conclusion, a lot of this stuff that we worked on is very similar to the concepts and the techniques that we're using in our robotics team. We kind of, I don't know if anybody saw the website, we recently just won the national championship, and we use a lot of similar techniques, if not the same techniques, to fabricate that robot. And so it kind of shows that JSU's engineering and technology program is kind of focused in the right direction to get not just the theory out of it, but actual like hands-on work done. And then I guess my acknowledgments. First guy was our main boss at Marshall, and then those were all the engineers and technicians we worked with, and then Mr. Margaret here at JSU. Any questions, comments?
You said that you use 3D printing in this.